This is problem number 90 from the Fundamentals of Structural Mechanics, second edition. Problem statement. Thick-walled sphere of inside radius 1 and outside radius 2 is subjected to an internal pressure of magnitude P. The principal directions of stress are the radial and tangential directions and are given by the following equations, where r is the radial distance to an arbitrary point with positive vector x from the center of the sphere, as given by this equation. We're asked to find A, the expression for the stress tensor S in the Cartesian coordinate system. B, we're asked to prove that the outside surface of the sphere is traction-free. And C, we're asked to find the body force B that must be present to maintain. So to begin, the first thing that we should see is that since we have a repeated vector, those can be considered, that should set us off that we have some kind of repeated eigenvalue. So we'll think of it in those terms here. Where we can set it up as a spectral decomposition using just two eigenvalues, where n3 is the eigenvector that corresponds with the eigenvalue mu3. So what we do is we substitute back in our stress. Instead of using the eigenvalues, we're going to assume that we have these sigmas are our eigenvalues. And that's actually our stress distribution. So we do a little bit of algebra. We cancel some things out, and we come up with things in terms of n3. An important thing to note here, though, is that n3 is the unit radial vector associated with the distinct eigenvalue sigma 3. So that basically is saying that n3 is the vector with respect, the position vector with respect to the radial distance to find the position of the area that wherever we're talking about in the sphere, which is going to become important in the second part when we're asked to show that there's zero traction on the outside surface. So anyway, we substitute that vector x over the radial distance into our equation. And we come out with our stress tensor S. For part B, we're asked to prove that the outside surface of the sphere is traction-free. And we know that we can find that traction by multiplying our stress tensor S by the position vector n, which is exactly what we do here. We're rearranging and canceling out terms as we know that we can, and we're left with sigma 3 n3. We know that we're interested at the outside surface, which is the radius of 2, so we plug 2 in for our r value, come out with sigma 3 equals 0, and we know that the traction at that point is 0 as well. Part C, we know that we're asked to find the body force B that must be present to maintain equilibrium, which we know must be the negative divergence of S because of that equation, which is expressed this way, which is just the partial derivative of each term in S. So here's S. We're going to get it into the correct vector format using x's instead of the e's and the n's. Here we are. This is the equation for Sij in vector format. What we're going to do is take the partial derivative of 5 different terms here. And you can see what each one of these are. It's just as you go down the row from left to right, we're taking the partial derivative of each term. So for the first one, we know we can see that the stresses are in terms of r, but we need the partial derivative in terms of j, so we need to do 2, which means we need to get r in terms of x. So we've done that here. We're taking the partial derivative of r with respect to x now, with each one of these x's, and we're left with xj over r is equal to dr over dxj. So for part 1, or I'm sorry, the first partial derivative, we take the partial derivative of that term, and as we cancel some things out, we recall that, and we're left with this as our first term. For our second term, or I'm sorry, this is our fourth term, we're doing the exact same thing, taking the partial derivative of this value, inserting in our different stress equations there, and we're left with that. For 5, it's the exact same thing. We know dxj over dxj is actually equal to 3, so it's the next step. We're going to recall that difference, plug it in there, and we're left with this for our fifth term. For our second term, we are doing the 1 over r squared, so we move all that to the left. We recall all three of these, and we do some simplifying, and we're left with this. For our third term, doing the exact same thing, taking the two partial derivatives. We're going to recall this. Kind of a long term there, but it ends up being 36p over 7r to the 5th xi. So here are all 5 of our terms, and when you add them up, you find that they're 0, which means that the body force present to, that must be present to maintain equilibrium must be 0 as well.